The standard way we think about quantum theory is there's a very important role played by the observer. There's an intricate mathematical apparatus, and this mathematical apparatus it engages in a form of quietism about what's really out there. But what it does is it delivers us a precise instrumentalist recipe for telling us what will happen when you do certain things. When observers do what's called a measurement on a quantum system, the theory furnishes a probability for getting a particular kind of outcome, right? That's what it does. But it doesn't tell us what's going on in between. So when you read a book about modern physics, you read a book about quantum mechanics, and the book says, well, the reason why this particular thing happens is because this electron's going like this, and a photon comes off of it and does that. As far as the standard way that we teach and formulate quantum mechanics today, the form of quantum mechanics you find in all the standard textbooks, all of that is just for color. All of that is just fables. The theory only says that when you have an observer, and the observer does this particular thing called measurement, then there will be these results with these probabilities, and that's it. It doesn't furnish anything else in terms of a physical picture. Now, that's the standard way that we teach it, it's in the books, but of course people have been dissatisfied with this picture for a very long time. And one of the things that Einstein was dissatisfied with about quantum theory, it wasn't the probabilistic aspect of quantum theory. It wasn't that God played dice with the universe. He could live with that. After all, one of Einstein's great breakthroughs was Brownian motion, right? Which was instrumental in us understanding the nature of atoms. It was, one of the papers that was part of his great year, his Annus Mirabilis in 1905. So probability wasn't the issue. For him, it was that there wasn't a metaphysical picture of what was out there happening between the measurements. So what one concern you might have is that maybe quantum theory is such a weird mathematical theory that any time you try to propose some kind of physical reality, a so-called ontology, Greek word again, right, for what's going on behind the scenes, it's going to be the kind of ontology that is inconsistent with the mathematical apparatus. So the worry was that the mathematical apparatus of quantum theory was over-determined. It was too constraining, and no picture you possibly could write down could be a picture that was compatible with quantum theory working. Right? This was the worry I think a lot of people may have had. And so the attitude was, we just shouldn't talk about what's going on. And this became known as the Copenhagen interpretation. The Copenhagen interpretation just says, our brains cannot understand what's going on between measurements. All we can talk about are measurements. Measurements are done by big, classical objects like us that obey classical rules of physics. And what's going on in between the measurements, we can't understand that. We have a mathematical apparatus for it, but we can't actually visualize it or write a picture down. And that's, we're trying to fill that picture. We're trying to fill that picture in.
Let me dissect that one word, which I think might mean two things. The word goes on between measurements. There's two types of betweens. There's between in quantum time, if you wish. There's between, of course, observations, but there's also between in quantum space. And the real numbers are a beautiful thing, but they might be completely fictitious because the physics of the universe don't obey real numbers. And then there's another, I'm not fond at all of the whole simulation hypothesis. Terrible hypothesis. But
I've known too many computer programmers, so I'm skeptical.
However, one interpretation of quantum physics is that there's just too much to compute. And therefore, you don't compute something, you have a lazy computer. That physics is basically running lazy computation. And
this is why there are all these uncertainty principles.
Computing everything.
Yeah, right.
And it's only when you sort of try to look up a variable that actually computes it. Can you debunk that idea? Sorry?
Can I introduce?
Of course.
I had a good point here.
What's your name?
Shresh.
Introduce yourself.
I'm a freshman at Northeastern. I recently started working at the Media Lab as a researcher, and I started getting into all of this. But what I was working on a few days ago was actually inspired by your post on Twitter about Lagrangian submanifolds. It was really impressive.
That is very cool. This moment must feel very good to you, right? Inspiring the young generation is so great.
What the student is referring to is my post on Lagrangian submanifolds, which went viral on Twitter, LinkedIn, and Substack. Feel free to follow me on Twitter at @ToeWithCurt. On LinkedIn, you can add me by searching for Curt Jaimungal. And for Substack, you can visit curtjaimungal.org. Links are in the description.
That is very cool. This moment must feel very good to you, right? Inspiring the young generation is so great.
So I have like a GitHub repo where I had like a bunch of Python notebooks which I was working on, and I used like a program synthetic approach to try to prove some natural laws using Lagrangian submanifolds, and it was actually working. Like I was proving conservation of energy, and both from the classical mechanics and the quantum mechanics side of things. And honestly, it was interesting because I don't think like the in-between factor is in fact being computed, like you were saying, because if you're able to compute like functions from like natural laws, the functions from natural laws, from such a probabilistic approach, it's so weird that you can end up with both approaches on like the macro scale and the quantum scale. So I think it's completely unsolved, the gaps between like everything that
In space, in time, or in computation?
in terms of computation.
Cool.
Yeah.
I'm Aviram.
Introduce yourself.
I'm an experimentalist. Can you explain what you mean by the in-between is not computed? Like all quantum mechanics does the in-between, right? It tells you, okay, in between you have a wave, it propagates according to Schrödinger's equation, and then if it interacts with a degrees of freedom system, whatever classical system.
It's nice to meet you. That's a very good question. Thank you.
There's some seats in the back. Do you mind coming and sitting on the white chair over there? The white cube?
Yes, I'll repeat the question. Yeah. So the question was.
Is this good or bad?
We have the tomatoes.
Notice there's a few more chairs.
Let me repeat the
speak
question.
up.
The question was.
Why didn't he ask?
Yeah. Right. So the question was, what the hell could I mean by saying that quantum theory doesn't say what's going on between the measurements? I mean, there's the Schrödinger equation, and there's wave functions, and there's all this apparatus, right? So what Heisenberg meant when he talked about the Copenhagen interpretation. So he wrote about the Copenhagen, he introduced the term the Copenhagen interpretation. It's a chapter in his book Physics and Philosophy in 1958. And the way he described it was he said, okay, classical objects, those have physical reality. We understand what they are. They're phrased in terms of objects that live in three-dimensional space. But we don't have the mental architecture to understand the reality, what's going on with quantum mechanical particles, tiny particles. So we use this mathematical formalism, but the formalism is not real. It's not physical. The wave function is just a mental construct, just a piece of mathematics. There isn't really a wave function anywhere. And so, but let me turn the question back to you. So, classic move. Are you suggesting that you believe that the wave function is a physical entity in the way that, for example, a chair is a physical entity?
I can bounce the question back to you.
Okay.
Is a gravitational field, for example, or whatever, any field, is that a real thing or not, right? You were taught in, ninth grade that there is a field. And what it tells you is that were you to put a particle in that electric field, it would sense a force which is measurable. Right?
Yes.
It's a field, a real thing.
I'm going to take a stand, and I'm going to say that right now I think that fields are metaphysically real. Fields are localized intensities that are distributed physically, metaphysically. They are real in the same kind of way that I think chairs are real or that you are real.
Now it's easy. Now it's easy to take that stand. I agree with you.
Yeah.
And now we're not in ninth grade. We're already.
Yes.
And we know that.
But there's a reason for it. But there's a reason for it. The reason I think that fields are physically real in the way that chairs are is because fields are intensities in physical space. And you can, they propagate energy and signals around through physical space. And so I have good reason to think that they are physical things. Now, why don't I think that wave functions, that Schrödinger wave functions are physical things? Where do Schrödinger wave functions live?
In the complex world. The math.
Not just the complex world. No. They live in
our minds.
They live maybe in our minds, but if they were purportedly to live in some kind of reality outside of our minds, where would that be?
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist.